Hey there, welcome to AP Statistics Quideo number 3. Today we're going to be starting with the basic question. Now the basic question looks at the probabilities of 6 different cars of the most popular vehicles produced in North America in 2000. So on the top you have the color of the car and the bottom you have the probability in decimals, not percents. Now the first question asks us to find the probability that you pick a car that is not one of the colors listed. Now in order to solve this, we're going to start by finding the probability of A, or that you pick a car that is one of the 6 colors. So in order to do that, you're going to add the relative probabilities of each one's in decimal, of picking each color in decimals. And you're going to use your calculator and get 0.705 or 70.5%. So that's going to be the probability that you pick a car and it has the color of one of the 6 colors listed. Then, in order to find the probability that it's not one of the 6 colors, you're going to find the complement of the probability of A, or probability A complement, which is the same thing as saying 1 minus the probability of A. So in this case, 1 minus 0.705, which would get you 0.295, or 29.5%. So that's your probability that you pick a car that is not one of the 6 colors listed. Part B of the basic question asks the probability that a randomly chosen vehicle will be either silver or white. So when solving this, you're going to assume, obviously, that they are disjoint or they're mutually exclusive events. So the probability of A, if that occurs, then the probability of B is non-existent, because if A occurs, then B cannot happen. So what you're going to do is first identify that the probability that you pick a card that is silver is 0.176 as listed in the table, and the probability that you pick a card and it's white is 0.172 also listed in the table. Then in order to find the probability that a card that you pick is either silver or white, you're going to find the union of the probability of A and B, and which is also equal to the probability of A plus the probability of B. So then rewritten down here with actual numbers, and you get 0.176 plus 0.172, which is the probability of A plus the probability of B, to get 0.348 or 34.8%. So that's the probability that you're going to pick a car and it's going to be either silver or white. Part C of the basic question is very similar to Part B, in that you're going to be finding the probability that either one of 2 mutually exclusive or disjoint events occur. So in this case, they're asking the probability that either both are silver and both are white if you pick 2 vehicles at random. So in order to solve this problem, you're going to start by finding the probability that it is silver, which we already listed as being 0.176. Now, to find the probability that it is silver twice, you need to multiply 0.176 by itself, or square it. And you're going to need to do that using your calculator, but I've already done it, so I found it's 0.031. Then you're also going to do the same thing for the probability of getting white twice, because the probability of getting it the first time would be 0.172, and the probability of getting it a second time would be 0.172 also. So to find the probability that both times are white, then you have to multiply both probabilities together, just as you did with the silver. So you'd be squaring the 0.172 to find 0.0296. Now, because these are both mutually exclusive or disjoint events, the probability that both are silver or both are white, you're simply going to add the squared probabilities together. Now, what you're going to end up finding is that you don't need to subtract by the overlap, because they are mutually exclusive and they cannot overlap, because if one happens then the other cannot, because you're not going to be able to pick 2 cars and get 2 white and 2 silver. So to find the probability that both are silver or both are white, you simply add the 0.031 and the 0.0296 together to get 0.0606, or 6.06%. And that's your probability that if you pick 2 cars at random, both will be silver or both will be white based on the data given in the table. Next, we're going to be looking at the advanced question. So the advanced question asks the question, will taking antioxidants help prevent colon cancer? Now, researchers have noticed that people who eat a lot of fruits and vegetables are also intaking a lot of antioxidants, such as vitamins A, C, and E. Now, they want to know that if these people who take a lot of antioxidants through fruit and vegetables are also having a lower rate of colon cancer because of those specific antioxidants. Now, in order to do so, they conducted a clinical trial of 864 people who were equally at risk of colon cancer. Now, these subjects were divided into 4 groups. Each one was given a different type of vitamin, a different type of antioxidant, and they were tested to see if they would develop colon cancer. So, the first question here asks, what are the explanatory and response variables? Now, the first part to understanding this is understanding what explanatory and response variables are. So explanatory variables are the variables that you're going to be changing. Those are usually going to be your X variables. It's something you're going to be manipulating in an experiment setting to try to evoke a certain response from the patients tested. So in this case, the antioxidant type is going to be your explanatory variable because that's what's being manipulated in order to determine what response there is with regard to if there is development of colon cancer. Now, the response variable is what responds in response to the changing of the explanatory variable. So basically, the effects of the explanatory variable graphed out usually on the y-axis. In this case, the presence of colon cancer is the response variable because they're testing how antioxidants, or the modification of the type of antioxidants one receives, affects the presence of colon cancer. Okay, so part B of the advanced question asks us to outline the design of this experiment, and they give us the best judgment to decide the group sizes. So I gave an outline for exactly how I believe this experiment should go. So first, you're going to number the subjects 1 through 864 in order of last name, then if there are any same last names, then the first name. Now, while this isn't random, it's just going to be simply giving them a number and not having confused people with names. Then you're going to be randomly assigning them to groups. Now, I suggest doing this using a random number generator, in which you pick numbers 1 through 864 randomly using this generator, and the first 216 picked go to treatment 1, which is beta-carotene, the second go to treatment 2, which is vitamin C and E, the third 216 go to treatment 3, which is all 3 treatments, and the fourth 216, or the final 216, go to number 4, which is the placebo. Now, I'm not saying 1 through 216 go here, 217, so on, go there, and so on and so on. What I am saying is that you will randomly be put into a group based on if your number is picked using the random number generator. Now, oftentimes you will get repeat numbers through the random number generator, but every time that you see your number after the first time, it can be disregarded because people cannot take place several times in one group or cannot take place in several groups. That would not be effective. Now, once they're effectively randomized and put into groups, they're going to be separately observed for 4 years for colon cancer development. Now, this is going to be able to be very beneficial to those who are researching this, as they're able to see clearly who is going to be developing colon cancer without any outside influence, as none of the patients know what treatment they're getting, and as long as they're all equally prone to developing colon cancer, there shouldn't be any discrepancy between the groups. So you should really get a clear picture of how each type of treatment affects development of colon cancer. Okay, so for part C of the advanced question, we're going to be looking at the random digit table in the back of our textbook to determine 5 people that are going to be picked at random for the beta-carotene group. So the beta-carotene group, if you remember from part B, was the first treatment group. So it's the first 216 people randomly selected from the numbers. Now, when you're using table B is just a random digit table, as I said before. So it really just gives you a bunch of truly random digits that you can use to decide the order of things and decide who gets picked, stuff like that. So it says to start at line 118 and go across. And because you're dealing with numbers 001 to 864, you're going to be picking numbers in sets of 3. And if they fall within that range, you're going to be using them. If not, you cross them out, forget about them, never touch them again. You move on to the next one. So you're going to be picking the first 5 3-digit sets that appear from 001 to 864. So first one, 731, that works, good, you pick it. 903, that's outside of the range, so you can just forget about that. Next, 253, that's in the range, good. 304 in the range, 470 in the range, and 296. So that's 5 numbers right there, aside from the 903 that didn't work, that work for this range 001 to 864. So as such, subjects 731, 253, 304, 470, and 296 are chosen to be in the beta-carotene group because those are the first 5 numbers that fit the range that are on line 118 of the random digit table that we're going to be using for the treatment 1 and group 1. Okay, so next we're going to look at part D. Now part D says that the study was indeed double-blind, and it asks us what this means in the context. So a double-blind study generally just means that both the subjects who are taking this survey or the experiment, along with the people who work directly with the subjects, are unaware of who's getting what medicine, who's getting what treatment, and who's receiving the placebo. So that way, it prevents the expectations of those involved from affecting the diagnosis. So let's say I expect the vitamin C to work really well in preventing colon cancer. Well, I might diagnose somebody in a way that kind of proves my expectation, proves my hypothesis. But because it's double-blind, that means I don't know, they don't know, everything's completely anonymous, it helps reduce bias, and it helps ensure the accuracy of the data. So in this case, what we're saying is that those who are subjects of this treatment are not going to be aware of what they're receiving. They're just going to be receiving a nameless pill that it has no identification on it whatsoever. And the people who are going to be giving this pill, giving the medicine, are also not going to have any idea to make it completely blind and completely, as much as possible, unbiased. Okay, lastly, we're going to be looking at Part E of the advanced question. So Part E states that there might be some lurking variables involved that are making it look like the antioxidants in fruits and vegetables are causing the rates of colon cancer and the occurrence of colon cancer to be less frequent. Now, first, in order to understand what lurking variables might be present in this specific experiment, it's important to understand what lurking variables are. Now, lurking variables are other outside variables, outside factors that are going to impact the response variable in such a way that makes it look like the explanatory variable is doing that. It's going to be things that are not directly tested by the experiment, but are used to explain the occurrences of the experiment. So in this case, some lurking variables could include that more fruits and vegetables in one's diet also could potentially point towards, there could be a correlation with the overall health of their diet. So people who eat more healthy foods will probably include more fruits and vegetables. And the overall healthier diet could be the lurking variable that explains why their rates of colon cancer are lower. So that's one. Another is that fruits and vegetables contain other good stuff too. So other good components, aside from the antioxidants, like fiber. And increased fiber could be a factor, a lurking variable, that could cause the rates of colon cancer to be lower in those who consume more fruits and vegetables. So the fact that these are not directly tested by the experiment, but could influence the results of the experiment, make them lurking variables, and make them worthwhile for checking out to see how they impact the rates of colon cancer in these experimental patients. Lastly, let's look at the AP question. Now, the AP question states that there are 2 antibiotics present that can help cure ear infections in children. Now, antibiotic A, treatment A, costs $50 and is 60% effective as stated by the problem. Antibiotic B, or treatment B on the other hand, is known to effectively treat the patient 90% of the time. So it's 90% effective, but it also costs more. It costs $80. Now, they work independently of each other. They can be consumed at the same time, individually, whatever. There's not really any real restrictions on the consumption of these medicines. Now, there are 2 plans of attack, 2 plans of treatment that doctors often use for, or with these treatments for ear infections. So plan 1 says treat with antibiotic A, and if it's not effective, then treat with antibiotic B. Then conversely, plan 2, says treat with antibiotic B first, and if that's not effective, then treat with antibiotic A. So the first question asks if a doctor treats a child with an ear infection using plan 1, what's the probability that the child will be cured? So that's saying that either that treatment A works or that treatment A fails and B works. And then it also asks the same for plan 2. So if you look at plan 1, you see that you're going to see that probability of A is that the patient is cured with treatment A first without having any influence from treatment B. Now that probability, as stated by the problem, is 0.6 or 60%. Then the probability of B is going to be that the patient is cured with treatment B after A fails. So that's going to be the complement of A, or how much A fails, which in this case is 0.4, times the probability that B works, which is, as stated by the problem, 0.9 or 90%. So when you multiply those together, you get the probability that B occurs given that A failed, or 0.36. Now, in order to find that if plan 1 works either way, whether plan A or treatment A ends up working or treatment B ends up working for the patient, you're going to find the union of the probabilities of A and B as listed above. And now you don't need to end up subtracting the intersection of treatments A and B, because these 2 are disjoint. So you can't have treatment A working and treatment B working, because if that happened, you would need to use both treatments, and it'd basically be ineffective otherwise. So in order to find the probability that plan 1 works, period, either way, then you're going to add the probability of A and probability of B, which we found above, as 0.6 plus 0.36. So that probability that treatment 1 will work, or plan 1 will work, is 0.96 or 96%. Then you're going to look at the same thing for plan 2. Now, just like above, we're going to label our probabilities. So probability of A is that the patient is cured with treatment B first, and as listed in the problem, that is 90% or 0.9. Probability of B is that the patient is cured with treatment A only after treatment B fails. So that's the complement of treatment or the probability of treatment A, which is 0.1, or as we listed before, 1 minus the probability that occurs, and times the probability of B working, which in this case is treatment A, which is 0.6. So when you multiply those two together, you get 0.06. Now, when you're finding the union of these two, that is stating that plan 2 works either way, whether it's treatment B that works or treatment A that works. Now, these two, like I said above, are disjoint, so they both can't occur together, so you don't have to worry about subtracting the intersect from them when you add them together for the union. So the probability that plan 2 works is going to be the probability that A works and the probability that B works given that A failed, and that is 0.9 plus 0.06, which equals 0.96 or 96%. So in both cases, the probability that the treatment is going to work and the patient is going to be cured is 96% or 0.96, but it just depends which one you're going to be which treatment you're going to be using first, and which one you're going to be using only dependent on if the first one fails. So part B of the AP question asks us to compute the expected cost per child when plan 1 is used and when plan 2 is used. Now this can be effective for determining the relative costs that are expected over a long period of time. So only if you use it over and over and over again, or if you use each plan over and over and over again, to determine the average cost, the expected cost for each person. Now the expected cost is also just another way of statistically saying the mean cost that's going to be observed given the probability of each event occurring. So without further ado, let's look at some numbers here. So the probability, first you're going to set up a chart. So for plan 1, the probability that you're going to be using treatment A and that treatment A only is the 0.6, because that's the probability that's going to work and you're not going to need any other treatments. So 60% of the time you're only going to need to spend $50 on treatment A as listed in the problem. Now if it fails, that means you're going to have to spend your $50 on treatment A and another $80 on treatment B. So you're going to spend a total of $130, but that's only 40% of the time when treatment A doesn't work. So when you find the expected value, you multiply the probability times the cost for each set and add them together. So 0.6 times $50 plus 0.4 times $130 is equal to $82. So $82 is going to be the expected cost of operation for treatment or plan 1, in which you receive treatment A, and if that doesn't work, then you receive treatment B. Now plan 2, you're going to go about doing it the same way. So first, you're going to look at the first event. So the first event is that you're going to need only treatment B, because treatment B is responsible for 90% of cures. So the probability that treatment B will work, and that's all you will need, so you won't need to go on to treatment A, is 90% or 0.9, and the cost of that would be $80. However, the other 10% or 0.1 of the time, you're going to need both treatments. So it's going to be the $50 from treatment A plus the $80 from treatment B that would fail in this case, so $130. But that's only going to be needed 10% of the time. So that's the probability that you're going to need to spend that much money. So when you set that out in the equation as like you did above, you're going to say 0.9 times $80 plus 0.1 times $130 is equal to $85. So in the long run, in the law of large numbers, you're going to see that the average cost or the expected cost of using plan 2, where you use treatment B, and if that doesn't work, you use treatment A, is going to be $85, which is $3 more than the expected cost of plan 1. Now, when you look at part C of the question, it asks, which would you recommend to a patient? Well, of course, because it is cheaper, I would say go to plan 1. However, you want to consider how effective each one is. So when you look above, when we solve this above, you find that both plans are 96% effective. Whether you start with treatment A and then go to treatment B, or you start with treatment B and then go to treatment A, they're going to be 96% effective. So because they both have the same effectiveness rate and plan 1 is $3 less expensive, it makes the most sense to go with plan 1 to save the patient the most money and to make sure that it's absolutely positively most effective, because that's the most important factor when taking into account patient health.